Okay, so this is a question about the relationship between location, velocity, and acceleration. So, if s is the displacement of a particle in one dimension, then the derivative of location is equal to velocity, and the derivative of velocity is equal to acceleration. So all this should be pretty familiar. So we're going to be using these to answer these questions. The problem says, if a rock is thrown upward on the planet Mars with a velocity of 10 meters per second, its height in meters after t seconds is given by this equation. So that's not made up. That really came from the constant downward acceleration on Mars is some magical constant of nature. Just like g equals 9.8 meters per second is a constant of nature on the surface of Earth, there's some corresponding g on Mars, and then you take the antiderivative of that twice, and with some assumptions about what the initial velocity and initial location are, that's what generates this equation h. But we don't really care about all that crap until the last part. So A says, find the velocity of the rock after 1 second. So what could be easier? So it's just h prime of 1. Okay. But what is h prime of 1? I guess we should find h prime. So that's going to be 10 minus, the 2 comes down, and 2 times 1.86 is 3.72. So that's what that is. And so h prime of 1 is just going to be 10 minus 3.72, which is 6.28. And what are the units there? That is meters per second. So it's kind of fun to think about what's physically happening. So at first, the person threw the rock up at 10 meters per second, and then it's slowing down the whole time, right? So it's eventually going to have zero velocity, going up when it reaches its maximum height. This question B is almost like a trick question. When will the rock hit the surface? That has nothing to do with the derivative, or it's not directly related to the derivative. This is asking something about the original question, the original equation. It's just saying, when is it going to be true that h is equal to 0? So set up that equation. So 10t minus 1.86 t squared equals 0. And you can factor out the t here. So t times 1 minus 1.86t equals 0. And so this t is telling you that 0 is a solution. So we know that at time 0 the rock is like in our hand, which I guess we're imagining is height 0. And then this other part, this other factored part, is saying at what time it's going to land. So you can solve that separately. So set up 10 minus 1.86t is equal to 0, and then it's really easy to see that t has to be equal to 10 over 1.86. And if you figure out what value that is, it's approximately 5.4. Right? So the rock hits the ground 5.4 seconds after it's thrown. Now let's look at C here. Okay, so there are two ways to do part C. The honest way is to figure out when the velocity is equal to 0. So you just figure out h prime, set it equal to 0, and solve. So why does that make sense? That's because the rock is going up, and as it goes up it's slowing down. And then when it reaches 0 velocity, that's going to be when it's at its maximum height. And so that'll be the answer to the question. You could use this value to cheat because going up and coming down are totally symmetric. So if to go up and come down takes 5.4 seconds, which it does because it's saying when does the rock hit the surface, so it goes up and comes down in 5.4 seconds. So by symmetry, the amount of time it takes to go up to the maximum height is going to be half of this, and so we know the answer is 2.7. But let's just use that to confirm the answer we get using calculus. So what is the derivative? I have it up here, you can barely see it. So there's the derivative. H prime is equal to 10 minus 3.72t. So let's set that equal to 0. and solve for t, and it's not hard to see that t has got to be equal to 10 divided by 3.72. And as we already know, this is approximately 2.7. Another way to see that is that, 10 over 1.86 is just twice this, because where did 3.72 come from? It came from doubling 1.86. And D is really irritating. I think I'm going to take this off on the final. I figured out what value that is, but maybe I forgot to write it down. Was I so dumb? Oh no, here it is. Okay. So what is this? This is just, you take the height equation and you plug in this special value, 2.7, and I actually use this more accurate value. And what comes out turns out to be 13.44. So that's just a lot of ugly computation when you don't have a calculator. It's kind of interesting to think about what it means, though. So initially the rock is thrown up at 10 meters per second, right? So you would think that it would get higher than that, but it's slowing down the whole time. And with an initial velocity of 10 meters per second, the highest it gets is, roughly 13.5 meters. So that's kind of interesting. And E here. So let me remind you what h prime is. So h prime is equal to 10 minus 3.72 t. Okay. So it's saying, what is g, the constant of downward acceleration on Mars? So on Earth everything is being accelerated downwards at 9.8 meters per second. And so there's some corresponding acceleration on Mars, and by these rules about displacement, velocity, and acceleration, you can tell that the answer here, acceleration, is just the second derivative of displacement. So the answer to E here is just h prime prime, which, as you can see, is just negative 3.72 meters per second per second. Okay, so this makes sense. Here we have on Earth, things are going down at negative 9.8 meters per second squared, and on Mars it's being accelerated a little more gently because I guess Mars is smaller. And that's the end of part 1, or problem 1.